Okay, today, in this hour, we will discuss the Doppler effect. And if time remains, I have been avoiding it as much as possible, but we can just discuss a bit about general relativity. Well, let's start with the Doppler effect. So what's the Doppler effect? I'm sure you have heard of it. Yeah, that's your everyday experience. If there is an ambulance passing by, it sounds different when it is approaching you and when it is moving away from you. Basically, what's happening is you have the waves, and the time we call the time between two waves is the period. The period is related with the frequency nu. Frequency is how many waves pass by at a given point in a unit time. And so if the source is moving for sound, so at a given time, the source is over here. Then it emits a sound wave. Let's say it emits this wave, which is also moving in this direction, let's say. At the next moment, after one period, that wave reaches this point. This is at t equal to 0. Let's say this is at t equal to 1 period. What will happen is this wave had reached over here. If the source was not moving, the next wave should appear over here. But now the source has also moved. So the source, let's say, is now over here. Since the source is now over here, this is the next wave. So this length, the length between the peaks of two waves, we also call it the wavelength. This is the wavelength if the source was not moving. And this is the wavelength if the source is moving towards you. So the wavelength will change depending on whether the source is moving or not. Well, of course, here we are talking about the source moving relative to the medium. You see, this wave is moving with whatever the speed of the wave is in the medium. And if the source is moving with the medium, in the medium, the wavelength will get smaller. Now, of course, things get a bit different when we have light. Because you see, according to Einstein, there's no medium of light. And for every observer, the light should be moving at the speed c. So here we should be a bit more careful about when we are specifying what we are talking about, whether we are talking about the reference frame of the source of the observer. Here there is the medium. We are implicitly always talking relative to the reference frame of the medium. But now in the case of light, there's no medium. So we should be a bit more careful. So let's look at the Doppler effect of light. Now, light will be created by vibrations. Any wave is created by some kind of a vibration. In the particular case of light, it is the charges that are vibrating, the charges making my source. It can be the electrons in the atom when they are making transitions from one state to the other state, as we will see in the future chapters. There's the charges that are oscillating and hence creating the wave. So let's assume we have a light source. In its rest frame, it has a frequency nu0, wavelength lambda 0, and period t0. Well, how are they related? t0 is equal to 1 over nu0. t0 is the time between two oscillations. Nu0 is how many oscillations you get per second. And lambda 0 will be c over t0, or c times t0. Or c over nu0. Lambda 0 is the distance between two waves. So between two waves, the time that has passed is t0. So the light, since it's moving with the speed c, this is the distance it will cover. So the wavelength is the c times t0. Now let's assume we have a light source, a planar light source. In the rest frame of the light source, there is an observer that is moving in this direction. You see, if you would imagine this as a source of sound, and this you are just driving parallel to the source of sound, there won't be any Doppler effect. Because the time interval between the waves will be the same, whether you are moving or not, and their arrival time will always be the same, so there won't be any Doppler effect. But now there will be a Doppler effect due to time dilation. Let's see. So let's just move to the reference frame in which the observer is at rest. This is my light source. Now the light source is moving in the opposite direction with the same speed. T0 was the time between the emissions of two peaks of the wave. But now the source is moving. There is time dilation. So according to the observer, the time between two peaks, let's say t, will be dilated. This will be t0 divided by square root of 1 minus v squared over c squared. So the frequency, well, the frequency, this is 1 over t, or nu is equal to square root of 1 minus v squared over c squared times nu0. This is the Doppler effect for an observer moving perpendicular to the direction of the propagation of the wave. And this is caused by time dilation. Because now, in this new reference frame, in the reference frame where the observer is at rest, the clocks on the source is slower. If the clock ticks, let's say, 3 times in the light source, it had ticked 5 times in the reference frame fixed in the observer. Do you agree? Now, the more complicated will be if the observer is moving. Yes? Well, let's see what happens. The frequency gets smaller. So let's say if the light source in its rest frame is emitting, let's say, blue, if the light source is moving, it will start emitting red, for example, depending on its speed. Now let's look at the other case. We have the light source. In the reference frame of the light source, we have an observer that is moving away from the source. In the reference frame of the observer is at rest, but the light source is now moving away from the observer. Now there will be, let's try to evaluate the period of oscillations observed by the observer. There will be two effects now. One, due to time dilation. The clocks on the light source will tick slower. So the emission of the next peak will be delayed. Second, well, when the light source emits the first peak, it starts moving towards the observer. Then it keeps moving away from the observer. So the second wave will be created further away from the observer. So it will take it longer to arrive. So we have to take into account both of those effects. Now let me still call T 1 minus V squared over C squared. No, 1 over this one. This is the effect of the time dilation. Let's say that at t is equal to 0, first peak arrives. Then at t is equal to t prime, second peak arrives. Now this t prime will be, on one hand there is the t. Already the light source waits this much to emit the second peak. So that's one of the reasons why the second peak arrives later. Plus there's also the other effect. The source had moved a distance v times t prime. Now v times t. The source had moved this much until it emits the second peak. And so it takes an additional time, Vt over c, to cover that additional distance. So this is the period observed by the observer. This is the time between the two peaks of the light source arriving at the observer. This is equal to 1 plus v over c times t, or 1 plus v over c divided by square root of 1 minus v over c, 1 plus v over c times t0. So t prime is equal to square root of 1 plus v over c divided by 1 minus v over c times t0. Or if you just take the inverse, the frequencies, nu prime would be 1 minus square root of 1 minus v over c, 1 plus v over c times nu, 0. So again, for example, if, as in this example, the observer is moving away from the source, or if the source is moving away from the observer, in that case, the observed frequency, V is positive, the observed frequency will be smaller than the its frequency in the reference frame in which it is at rest. So again, if this is a light source, if the light source in its rest frame is emitting some blue light, it will be shifted towards red light, which has a smaller frequency. Yes, your question. Well, you see, length contraction is when you want to translate from one reference frame to the other reference frame. So which length are we translating from one reference frame to the other one? Again, the question is, which length is contracted? You see, here I'm not using any length. I'm not translating any length in this reference frame to some length in that reference frame. I'm translating the time. There is one time over here, the frequency of the oscillations of the light source in the reference frame in which it is at rest. I am translating that time to this reference frame. I'm translating T0 to T. There I use the time dilation. But then that's the only thing I translate. If you look at over here, T is the time measured in that reference frame. V is the speed of the source of light measured in that reference frame. So everything here is measured in that reference frame. And what I obtain is also something measured in that reference frame. I'm not translating from one reference frame to the other one. So I don't, except then this one, I don't use my translation table. Well, let's see. What happens over here? Lambda is C over nu. Or this is C over nu. This is 1 over square root of 1 minus V squared over C squared, C over nu 0. 1 over 1 minus V squared over C squared times lambda 0. The wave, now in this example, the wavelength gets larger if I go to the other reference frame which is moving relative to my source. Wavelength. Wavelength of the wave. You see, there is this wave, the light. I have this light source in the reference frame in which the light source is at rest. This wave has some wavelength, that I call lambda 0. Then there is the other observer, which looks at this light source. Here is the light source is moving parallel to me. So, according to this observer, the wavelength is longer, not shorter. If you like, you can work this out. Okay, you were expecting some length contraction, but there's also time dilation. You have to combine those two factors. This one. Well, you see, here I'm not translating any length from one reference frame to the other reference frame. So, which length contraction? This is the complete formula. But you see, if you want to compare the wavelength in two different reference frames, you also have to take into account the time dilation. You see, this is the translation law for the wavelength. But in the way I derived it over here, I don't need any length contraction. It's not needed. I started with how translating the period, or in a sense, translating the frequency. And then I corrected it. This is the translation I use. In this expression, which is the period perceived by the observer. This is the period perceived by the observer. Here, there is no translation. Why shouldn't it? There is only the translation of time. I just define the wavelength dependent on these quantities over here. This is the correct expression. I don't need any length contraction. Of course, it will be again a nice exercise for you. Can you relate this to length contraction? Indeed.
If we use the length equation, we should use both combined together. I don't understand why it should be combined together, whereas we consider one of them is stationary and the other one is not. So how can we combine each length contraction and time dilation?
Well, let's see. Listen, okay. When we use the time dilation, length contraction, we said that we have to be sure that we length contract the length measured in the reference frame in which the object is at rest. Okay, so let's just imagine these two cases. First of all, here there's just a wave. So let's just imagine 2 points like the one we did in the spaceship. You see, we have these two ships, in this case, 2 points. 2 peaks of this light are at 2 successive peaks of the light are at these points simultaneously in one reference frame. Okay? Then I measure the length difference. I measure the distance between those two. That gives me the wavelength. But if I go to the other reference frame, the other reference frame will say that, no, those 2 peaks are not at that point simultaneously. So this problem is, in fact, it should be almost exactly analogous to the spaceship problem we had.
So why should we combine both? So why should we combine?
Because we did it also in the spaceship case. You have to be a bit careful about your definition. Well, when you say, if I say use Lorentz transformations, I am in fact saying use both length contraction and time dilation properly.
In this sense, we are accepting that one is stationary.
You see, here we have 3 things. Also keep in mind that here we have 3 things. And the third one, which is the light, which is moving with the same speed for every observer. I don't have 2 things here. I have 3 things. I have the source, I have the observer, plus the light. That is what is making it a bit more complicated. And the light is moving relative to both observers. That's what I did. What do you mean directly? Okay. You can, but you have to be a bit careful. Again, as I said, just like in the case of the ships. You can do exactly the same treatment here. just make sure that you identify your two events properly, so that they will give you the period and the wavelength.
If the source or the observer were accelerated?
No acceleration. Not yet. If you want, you can compare two different observers with two different speeds. But no acceleration. Because then we should go beyond inertial reference frames. No question now? Okay. Well, let's see. Do we use this? Yeah, of course, I mean, the police uses this. Basically, I mean, how the radar works, it sends you some electromagnetic wave and looks at how much the wavelength changes on the reflection, and hence it can determine your speed. But also in astrophysics, we can use it. You see, if you look at now how do we use it in astrophysics? We will see that when you have some elements, they emit particular lights, lights at particular frequencies. If you look at I'm sure you have seen the prism, effect of the prism on sunlight. If you have sunlight, it will just spread as a rainbow colors. So, I mean, we will be discussing this spectrum in more detail in the future, in the following weeks. But furthermore, if you look at the spectrum of sunlight, you will see that the spectrum is not really continuous. Especially if you look at it with a microscope, you will see that there are dark lines. At certain position, let's say, this is the spectrum. You just have the light beam passing through the prism. It will split into colors. You take the photograph of the colors, and this is what you would see. It will be more or less uniform, except then some dark lines. And from looking at where the frequencies of these dark lines, in fact, for every element, there are characteristic dark lines. So we know that most stars are made up of hydrogen. Hydrogen has characteristic dark lines. So if you look at the spectrum of the sun or any star, you can identify the lines of the hydrogen. But the problem is not the problem, but if, let's say, this is some particular line corresponding to a hydrogen for one star, this is essentially let's say, the wavelength. If this is for sun, if you discover a similar star, we see that it is shifted. Well, we know that it is the same line, basically because all these lines, they come in families. So you see, if there is one such line over here, another one should be here, another one should be here, another one should be here, let's say. And here, for the other star, we observe exactly the same family. So we know that they correspond to the same family. But the wavelength is shifted. It is shifted to larger wavelength. This is why we call it redshift. And once you identify how much the light from a star is redshifted, well, you know the new frequency. You know what the frequency should have been in its rest frame, because you know that it's from the same element. So you know its frequency in its rest frame. You know the observed frequency. The rest is just solve this equation for V over C. So you can identify, by looking at how much the spectrum is redshifted, you can identify the speed of far distance stars. So this is how astrophysicists measure the speeds of stars. They don't really observe how much they are shifted in a given amount of time, but they just look at the redshifts. From the redshift, they can identify the speed. And in fact, it turns out to have an interesting result. They have other means of determining the distance of the star. So let's say you can determine the distance of the star by some means. You can also measure the speed of the star by using this redshift. And what happens is, if you just put the stars on this plot, this is what you get, more or less. Well, there is a large scatter, but nevertheless, it's more or less a straight line. So the speed of a star or a galaxy is, let's say, on the average proportional to the distance from us multiplied by some constant h. H is called the Hubble's constant. So the further away stars, the larger the R is, the faster they are moving. Well, in fact, you can just invert this. R is equal to 1 over h times v. Just compare it with R is equal to vt, motion with constant velocity. So essentially, what that tells us is that if there is a t equal to 0, the stars that are moving faster from us, they should be at a further away distance. So this is the age of the universe. If you would somehow reverse the direction of time, all these stars that are moving away from us, they will be moving towards us, and after a time 1 over h, all the stars and galaxies, they will just collect at a single point. So that is what we call the Big Bang. We don't really know what happened there, but nevertheless, it still has a name. Well, we don't know whether this 1 over h is changing or not, or how much it is changing. The universe might be accelerating. In fact, we do expect the universe to be accelerating. You see, the model we had until a few years ago, let's say, that whatever happened at Big Bang, we don't really know. But after that, the universe started expanding. So everything started moving out. And so there's but still there's the gravitational acceleration. So all the mass will try to pull it back. So they should decelerate. And they should decelerate, and depending on their initial velocity, if their initial velocity is faster, initial speed is faster than the escape velocity, they will decelerate. Nevertheless, they will keep moving out. Or they can stop. If the initial speed was lower than the escape velocity, they should slow down, stop, the universe should stop, and then it should just everything should start moving together, moving to a collision. So that's what we call the big crunch. It depends on how much mass we have and what was the initial speed. And the measurements just told us that it was almost, the initial speed was very close to the escape velocity. We didn't know whether it was larger than or smaller than that. But then, I don't remember the date now, let's say within the last 5 years, there had been measurements that show that the universe is not slowing down. So it seems to be that initially the claim was the universe is accelerating. So then the question was, what is causing the acceleration? The gravity should slow it down. It should decelerate, but it does not. The new result still shows that it's definitely not decelerating. It might be moving at constant speed, but nevertheless it's not decelerating. So there should be something that is pushing the universe out, and that is what we call the dark energy. We don't even know what that is. Those are some of the open questions we have about the universe. Now, at least there are some things we know. Let's say we have an explanation for, let's say. So why do all the stars run away from us? I mean, they are not really running away from us. I mean, if you would go to a different galaxy and look at the stars around you, you would see exactly the same picture. Everybody would be running away from you. So the current picture we have is just like this balloon. I think we had discussed this before. It's just like this balloon. The stars, more or less, they are fixed on the surface of the balloon, but the balloon is expanding, so that every star or every galaxy sees the other galaxies moving away from it. Of course, there is still some motion relative to the surface of the balloon, like we will be colliding with the Andromeda galaxy within the next 5 billion years. So we are moving towards each other. But on the average, the galaxies, stars, they all seem to be moving away from each other. And that's why we think the universe itself is expanding.
It makes sense, but does stars also expand?
Do stars expand? No. You see, this is to answer that question, this is a nice analogy. Just imagine this. Imagine yourself on the surface of this balloon, and you hold hands with your friend. As the surface will be expanding, well, you will just move towards each other. So you will not be moving with your friend. You will not be moving away from your friend. So the forces that keep the star determines the shape of the size of the star. They will make sure that the star is not expanding. But this is, of course, true only if the balloon is not expanding at the speed of light. So you see, nothing prevents the balloon from expanding at the speed of light. None of the stars can move faster than the speed of light relative to the balloon. If the balloon starts expanding at the speed of light, if the expansion of the universe is accelerating, eventually the universe will be expanding faster than the speed of light. In that case, nothing will survive.
You said that some very distant parts of the universe get away from us faster than the speed of light.
Yes, we don't see them.
Approximately how far is that?
Well, look up the Hubble's constant. Look up the Hubble's constant. You want V to be c, and you will find the distance. Approximately 14 billion years, light years.
So, theoretically, if we had this is also a silly question, but if we had a very long rod that is 16 billion light years long, that rod will not hold itself together.
I'm sure you will have more problems even for a shorter road, but yes.
Expansion of space means there.
Well, let's see. Let's suppose that you are 14 billion light years away from me. That means you are moving faster than the speed of light relative to me. Now you are not moving faster than the speed of light relative to me anymore, because you are no longer 14 billion years away from me. So you see, whether the rod will be torn apart or not, it depends on the local properties. You see, it won't be possible to keep a fixed length rod between you and me. If we hold it, it will definitely break apart. But if at an instant we just put it there, well, it will either move relative to me or relative to you. So we will not be able to hold it. But it will probably move relative to both of us. Other questions? Well, let me just mention a couple of words about the general theory of relativity. Well, you see, special theory of relativity, it just arises from one of the postulates was if you are in a closed room, let's say, and if this is an inertial reference frame, it's moving, let's say if it's an inertial reference frame, no experiment that you can do in that room should be able to tell you whether you are moving or not. That was the initial postulates of initial starting points of the special theory of relativity. Well, of course, you can say that, well, if I'm accelerating, then I can tell that I am accelerating. Just imagine closing your eyes. You are inside the car. If you suddenly feel a force that is pushing you backwards, then you will say that, no, okay, I'm now accelerating. You can definitely say that you are accelerating. But the general theory of relativity says, no, you cannot tell it. Even if you are in an accelerating reference frame, you cannot tell, of course, assuming this very small region and that you are not looking outside. No experiment in that room, in that reference frame, can tell you that you are accelerating. Then, of course, you can complain. How come I feel the force. Now, the thing is this one. Suppose you have this elevator. And you put this elevator in empty space, far away from everything else. And then you put a scale to weigh your weight. You try to stand on it. And then if the scale shows that you have some weight, then you will say that, okay, I'm accelerating, right? That is what you would say. And then conclude that, great, I'm accelerating. But Einstein says that, no, you cannot. You might be accelerating. Since you are not looking outside, it is possible that, let's say, a planet had passed by. You cannot distinguish these two. So either you are accelerating, according to some observer, let's say, or you are not accelerating, but you are under the influence of gravity. There is no way you can distinguish these two. That is what Einstein says. And this, in fact, he can say it because of the equality of inertial mass to the gravitational mass. So if these two are equal, well, you see, if the elevator is accelerating, then the scale will measure a force which is created due to the inertial mass. But if there is a planet passing by, the scale will show a force which is created by the gravitational mass. So that is why this assumption is crucial. And the current experimental bounds on that equality is also quite strong, almost as strong as the limits we have on the mass of the photon. So as far as we know, those two masses are equal. So what? Okay, one direct consequence of this is that gravity bends light. Once you make this, once you accept the, let's say, the proposition that in a closed room, you cannot distinguish acceleration from gravity, then gravity should bend light. Why? Let's say you are in a closed room. And let's say you are accelerating with an acceleration a, upward. And suppose there is a light source which is supposed to send a light beam straight to the other side. Well, the light for an outside, let's say there's an outside observer. For that outside observer, the light will just go straight. But as the light is going straight in that direction, the elevator is accelerating upward. So if you would just plot a couple of pictures, let's say this is at t equal to 0, the light beam is over here. At the next time, the elevator is over here, but the light beam is over here. At the next time, the elevator is, let's say, over here, the light beam is over here. And if you just translate it to what the observer in the elevator will see, it will just see the light beam to bend. So this is in the picture when there is an accelerating elevator. But if acceleration and gravity are the same thing, if these two things are the same thing, so if under the acceleration light beam should bend relative to the observer, for a non-accelerating observer, under the influence of gravity, light should also bend. Otherwise, the observer inside the elevator can tell whether he is under the influence of gravity or whether he is accelerating. And the light, as far as we know, it goes along straight lines. So when they say that, okay, the space-time is curved, what they actually mean is that assuming light goes on a straight line, that is a straight line on a curved space. So that is as straight as it gets. Anyway, we can continue this on the first hour on Thursday.